Thank you, Shar. Yeah. So so it's actually, it says, okay, so actually it saves me a lot of trouble that I do not have to prepare new slides. So I basically used the one I previously prepared, and I think we can take this opportunity to go through the profile functions of X-ray diffraction. Something I think is very important and very practical, something we haven't touched upon yet. Okay, so if you still remember, at the very beginning of the X-ray diffraction lectures, we mentioned that there are three things we need to pay attention to, right? The peak positions and the peak intensity, and the last one is the peak shape, the peak profiles. And those three can be correlated in a certain sense. And if you still remember, we touched upon the Bragg's law and also the scattering picture to understand when does diffraction happen, right? And that relates to the peak intensity. And also I said something about being cautious about the physical picture of a Bragg's law because it's not very rigorous. A more accurate picture is still scattering, meaning that scattering happens when the scattering vector is also a vector in this reciprocal space. That's the accurate physical definition of when the scattering happens, and also that's the beginning of understanding a lot of our more information about X-ray diffraction, right? Rather than just to picture it as something, some sort of reflection that a mirror reflecting lights, which is pretty shallow, I would say. Then we touched upon the peak intensity, and I think the number one concept that we always need to keep in mind is structure factor. The structure factor is the key, I would say, right? Structure factor is something that enables people to really solve atomic structure from the X-ray intensity. Everything really hinges on this relationship, right? How we can understand the position of thousands of atoms in the crystal, right, by simply looking at the X-ray diffraction peaks. And there are more details, but the core is a structure factor, which relates the atomic positions to their peak intensity we see. So in addition to that, there's some modifications. For example, the absorption of the atoms, they're moving, right? They're vibrating. So actually we have dampening, and we have atomic form factor, and we have the B value factor, which relates to both the thermal and the static disorder. And those two are dampening intensity. So we always observe smaller peaks at high angles, right? So that's kind of a general trend. And also the neutron differs from the X-ray in the sense that the neutron does not have the effect of atomic form factor. It's only influenced by the disorder factor, right? So that's some sort of benefit of using neutron. And also we explain why we need a high flux, high energy X-ray to really to do the PDF, because we want to access the high Q range. We always have a very weak peaks at high Q, so we need to have a high energy because the lower the energy, actually the higher the Q you can achieve. That's related by the mathematical definition. And also, if you have a high flux, then we have a much better signal to noise ratio at a high Q. And maybe there are also some other details about intensity, but we'll just move to the peak profile. Peak profile is something describing how the peak shape changes as a function of 2 theta. For example, are they symmetric? Are they broadened, very sharp? There are those kind of features. And it is important because, as I mentioned, it's highly correlated to the peak intensity. So depending on how well we define the peak shapes, that relates to how accurate we can, obtain the peak intensity, right? And we know peak intensity relates to the atomic position through the structure factor. So that's basically saying that determines how accurate we can solve the structure. Right? So profile function is very important. And also, I want to say a few more words. I don't know if you ever wonder, why we pay attention to profile function specifically for X-ray diffraction. Seems that for other techniques we do not really talk too much about the peak shapes, right? For example, for the XPS, for XAS, or for other spectroscopy tools, we normally do not care that much. We usually regard them as either a pure Gaussian or pure Lorentzian, or some sort of simple pseudo void, which is basically a linear combination of Gaussian and Lorentzian. We'll talk about what is Gaussian and Lorentzian later. Yes, so I would say it is true that in some ways, profile function is kind of unique to X-ray diffraction, that people want to study it with a lot of details and depths, right? So, and also there's a lot of works in this area, and I'll mention that some of them actually came from Bing-Yale, which we should be proud of. So the true physical origin of our, that we need to understand the peak shape accurately specific for X-ray diffraction has a lot of actually the backgrounds. So, but we probably would not just to discuss, we will not elaborate at this point, but I hope you can keep in mind that it is something kind of specific to X-ray diffraction. And as shown in this slides, currently there are 3 ways to describe the X-ray peak shapes. So those come from decades of works by a lot of smart people. And they're generally speaking, we have the fundamental parameter approach. So this is a sort of physics intensive approach, meaning that people try to understand every detail of the X-ray diffraction process. For in the context of synchrotron, people want to understand everything from the optics to the sample setup to the detector, everything accounted, so that everything can be described by a certain sort of function of equation, right? So everything has its own physical meaning. It's very rigorous, but you can easily imagine that should cost a lot of work, a lot of effort, right? And it could be very specific to owning a certain type of setup. The second one is empirical. So as I mentioned, people can use, for example, the pseudo void profile function, which is basically a linear combination of a Gaussian and Lorentzian. And this is very easy, right? It has only certain parameters that you can fit, and in many ways, it applies to a lot of our cases, including both the synchrotron or the LabX, right? So it's very commonly used, but apparently it's not very accurate, right? Because it doesn't really have a very strict physical origin for all the parameters that we want to fit. The third one is taking some sort of a combination of a hybrid of them. So actually it would respect the physics part, and also respects taking advantage of the efficiency of the empirical part. For example, people realize that the Gaussian part of the peaks is mainly contributed by the instrument, and another historical fact related to this is the first railroad refinement. So I think railroad refinement is very popular known these days, and the people who first pioneered this work is Robert Hugel, who is from Netherlands, and he was working at the neutron beamline. So the first railroad refinement was actually done neutron diffraction data, and was quite successful. That's because in the neutron setup, actually the peaks are mostly Gaussian. So he does not really have to care too much about the peak shapes at that time. And he simply mostly used the Gaussian shapes, and that modeled the pattern very well. But it will be problematic when it comes to the X-ray, right? So the Gaussian part is mostly instrumental, and people can describe this with parameters that have a well-defined physics origin. But the Lorentzian part is mostly contributed by samples, and we can imagine that can be complicated, right? Depending how your sample was prepared, is annealed or quenched, right? And it could have all sorts of defects, and all those things can be very specific, and it complicates the peak shape analysis. So there are three types of the peak shape approaches. We have been talking about Gaussian Lorentzian all the time, so I think they deserve a little bit of explanation. You may be already very familiar, but in case you're not, so we know, Gaussian is commonly used in statistics, a sort of distribution, and is characterized by this kind of exponential term, right? So we have this exponential term, and we have a quadratic relationship relating to the deviation from the equilibrium state, equilibrium position, right? So this is the typical Gaussian function, and the characteristic, as we see here, so this is a Gaussian, the blue one, is pretty sharp. So Gaussian peaks, they're very sharp, meaning that actually they have a very sharp abrupt increase at the equilibrium point, and then it decays very fast, right? So Gaussian peaks are sharp. That's kind of the feature. So for the Lorentzian, we see that it has a different mathematical definition, right? So Lorentzian doesn't really have the exponential term, rather it's kind of a reciprocal, but also having this kind of quadratic terms. So correspondingly, we can see the Lorentzian, the peak shapes, they are more broad, right? So the peaks start rising early on, then gradually increase to a point that is not very high in terms of their absolute intensity, then gradually decreases. So those are the graphical features of a Gaussian and the Lorentzian. As I mentioned, a very simple way to simulate the practical peaks is to construct a combination of them, right? Strictly speaking, they should be a convolution of the Gaussian and Lorentzian. It should not be a simple linear combination. And the convolution is actually a well-defined mathematical concept, so that we need to multiply these two functions at each point, and they're making an integral of the whole process. You can imagine that's a very mathematically challenging, and when it comes to application in computer softwares, it would take a lot of time and resources. So in practice, a much easier way is to construct a linear combination of Gaussian and Lorentzian using the so-called the pseudo-void, which is a basic linear combination of them, right? And in the context of doing X-ray diffraction analysis or doing railroad refinement, what we do is we try to find out this linear coefficient. So we want to understand, how much component, how much Gaussian is embedded in a certain peak, and how much Lorentzian is embedded in a certain peak. It may sound simple, But as I will show later, we need to keep in mind, and in practical analysis, this is actually two-seated dependent, meaning that for all the peaks, this adder is not the same for all the peaks. This adder is actually evolving, and we'll see, at least what's the trend it should be following during the evolution of this adder. Okay, so now we're coming to some practical peak shape functions used for X-ray diffraction analysis, the real refinement. So if you're using GSAS, which is a free, and you probably will come up with their peak shape function 2, maybe 3 something. I have been using GSAS for some time, but should be the first 2 or 3 functions, and they are based on their the Caglioli. And this is the Italian, has Italian origin. So the Caglioli function is basically describing their both the instrumental contribution and Lorentzian function to describe their XRD peak shapes, and it's very widely used in GSAS. I think now has been developed into GSAS 2, which is also free, and so if you're interested, you can download and play with that. But as I mentioned previously, I think the general trend, at least in our group, is still to try to use the Topaz, which is much more powerful and flexible. But it doesn't really hurt, without us understanding the fundamentals. So this is the formula for the Caglioli peak shape function. So we see for this Gaussian part, it actually have their 3 parameters to be fitted. So those 3 parameters are some parameters to be fitted during a real refinement. In the GSAS interface, I think you'll see something like GU, GV, and the GW, and those stands for their UVW parameters relating to the Gaussian part. You will also see their LX and LY. So LX and LY are their parameters defining their Lorentzian part of this peak shape function. Okay, and also, as I mentioned here, this HG and the HL, they stands for their half width, the full width at half maximum of that peak. And those are to be fitted during the refinement. And there, we can see Caglioli is just simply a type of pseudo-void, meaning that for each peak, it is assuming that the peak shape is some part of this and some part of this. It is simply at HG and plus the 1 minus adder HL. Okay. But that's certainly not enough. And so the pure Caglioli function was used in the very early days of the refinement. And people realized that it's just far from satisfactory. And some improvements were made on this function. And so I cited 2 papers here. And I would say they're all from Brookhaven. And actually, I think this is some sort of indication that Brookhaven, especially the physics department, they made a lot of contribution to the diffraction community in a lot of ways. And this is I think they're 2 of the great examples. So this slide was prepared, I don't know, maybe 3 or 4 years ago or something. So it was 2,600 citations at that time. Probably they're over 3,000 or even more today. And another thing I want to mention that nowadays, especially people who do their their material chemistry or their bio-based, they do not really care too much about the methodology. So in other words, people nowadays who use real refinement rarely cite the real refinement methodology, not to mention those detailed the approaches kind of additional to the rural climate. So that's some sort of a trend in the community. But I think we need to respect those works. And this first one is the so-called the TCHZ. So it's actually, it has the origin from horses, right? So T stands for Thomson, and C stands for Cox, and HZ stands for Hastings. So those people, they basically came up with ways to improve their caglioli, and it actually can fit the pig much better than the original caglioli term. And a further improvement on this is people start to address the low angle peak asymmetry. And this is very typical for the actual diffraction. If you have some low angle peaks, usually they are more asymmetric compared with median or higher 2 theta peaks. So an improvement from the TCHZ and to the so-called FCJ is actually the correction of the low angle, the peak asymmetries. As I mentioned, right, people have to do that because only when people can model the peak shape very well, then can they obtain the accurate intensity. So this is some sort of effort people devoted to that direction. And FCJ stands for the Finger, Cox, and Joseph Cott. So this is the origin of this kind of a term. And those two terms would be seen in the context of the topaz, and also in the context of the GSAS. I think at least starting from the third version or fourth version of GSAS, at some point GSAS start including TCHZ into their profile functions. So maybe that's profile function 4 or 5 something. And further, there was an incorporation of a FCJ correction addressing the low angle asymmetry, peak asymmetries. And so that was probably also introduced in GSAS profile function 6 something. But these two approaches, they were adopted in the topaz profile function. And the topaz profile function actually considers both, and even makes a more improvement in modeling the peak shapes. So, so next time if you see TCHZ coming up in the topaz script somewhere related to topaz application, it actually stands for this sort of a profile function as improvement of caglioli. So this TCHZ function is I would say is a new starting point compared with caglioli, right? It has origination from caglioli, but it has much more improvement. So let's say, well, what's improved? It still inherits the general formula for the Gaussian part, but now we have additional term here relating to Z. So so you probably will see that in GSAS, it will have additional GZ parameter, which coming from the Gaussian part of this profile function. But we still see the similar form, right? And also for the Lorentzian part, it's basically the same, right? You still have the XYZ defining the Lorentzian part. And now the error, as I mentioned before, error is not a fixed number. Right? It's actually something evolving, and there is how it evolves has this sort of a correlation with this parameter Q. What Q means is basically defining the percentage of the Lorentzian part in the whole peak. So how much Lorentzian each peak has would define, there's this more complicated error, and that defines actually how G and how Gaussian and Lorentzian are combined together to form the final peak shape. Okay. Some other more comments relates to the GSAS computation. So okay, GP. So I kind of forgot. So in GSAS, this Z parameter is actually it's called a GP, and it provides, the GSAS itself provides some sort of grain size estimation. This is a very simple one. It's basically just totally based on the Shor equation. So we know Shor equation relates the peak width to the grain size. By grain size, we mean the coherent diffraction domains. So they have this sort of a formula to calculate what kind of grain size it is. So those parameters are Lx is fitted, right? Pi is constant, and the lambda is the wavelength, and k is a Shor constant. And people normally just use k equals to 1 as estimation. But this sort of estimation is very rough. It's not that accurate, because we know that if you do a statistical counting of the particles, you know that they do not, fall in within a very narrow range. They have some sort of distribution, right? If you count the particle size of any samples we have, they should have some sort of a distribution. And so, and to be more accurate, actually, people need to define what do they mean by the grain size, right? People normally cannot show a graph and say, this is the distribution of my samples, but people would either use, for example, their volume weighted, right? People actually use so-called volume weighted the grain size, which has a more accurate definition, because the volume weighted grain size really it has embedded information about your distribution of your particle size, and very apparently that cannot be calculated simply by the Shor equation, right? And that relates to more complicated peak shape analysis. Maybe something could also give rise to a topic that we can discuss at some point. And here I'm showing a typical the profile function variation, especially the width, how the width varies as their function of the 2 theta. So this sample is AMC, and the data was taken 7 or 8 years ago. It was taken at Lysos-1, was a powder X-ray diffraction beamline. So we see there are some derivations, but clearly the general trend is that actually there's as the 2 theta increases, the peak width increases, right? So this is a general trend, and this trend is valid for most of the samples that we will see, or most of the X-ray diffraction data that we will see. And in fact, if it is a very perfect sample, let's say if it's a single crystal, right, it has no defects, grain boundaries or whatsoever, we will see a very clear trend that it doesn't really have this kind of a scattered behavior. And this kind of a scattering behavior is already indicating that our sample is not so perfect, right? But who has the perfect sample? That's an easy question. It actually is some sort of hint of the possible defects in the sample that causes some of the deviation from this general trend. And we'll touch that a little bit. Okay, and also we can see that this kind of a trend, which is described by the pseudo void function. This was fitted in the GSAS at the time. I was using GSAS. So it was fitted in GSAS. So GSAS gave their TCHZ profile function, and they're using that profile function. It has defined this kind of trend, and we can see it has contribution from the 2 components, right? And you see the Gaussian part has this kind of variation, kind of curved variation, but for the Lorentzian part is simply just a linear, right? So Lorentzian part has this kind of a linear relationship between the peak width and the 2 theta, but the Gaussian part have this kind of the curved features. And that in fact brings about the Williamson-Hall plot, and maybe you are already familiar with. In case you didn't use it before, it should be very easy to understand. So it takes advantages on the fact that the size part, and the spring part, even though they both contribute to their peak broadening, but they have a different variation relationship with the cedar. So we know that if you have a small sized sample, right, so that will contribute to the peak broadening. But if you have a strain in the sample, it will also contribute to the peak broadening. And this is so-called Williamson hot plot. It's basically a way to differentiate these two contributions. Why it can do that? Because their size broadening basically has this kind of a sec of the reciprocal of the cosine theta relationship with the how it changes during the two theta, right? And in contrast, the strain has this kind of tendency to variation pattern. So they changes, even though they both changes, but change it in very different ways. And what Williamson Hall did is actually, it's very simple. It's simply just plotting their figure in a very different way, such that the information will be decoupled. So what we mean is that instead of plotting the x-axis as a theta, we plot as a sine theta, and the y-axis, instead of the full width at half maximum, we multiply it by the cosine theta. And in this way, we obtain a linear relationship between these two parameters, and the slope is actually defining the strain of the material. And this kind of intercept with the y-axis is defining the grain size. So here I'm using example, and this example actually comes from my PhD work when I was working on the spinel. I was working on high voltage spinel. So I synthesized this is a annealed one, which went through a long time annealing, meaning that actually it will remove a lot of defects, right? And also more likely to give a disorder, and the structure is relaxed, which means actually the strain should be small in this case. And for this one, is actually it was kind of quenched. So kind of on purpose, we introduced some sort of a strain in a sample, and we can see that those two samples have a very similar grain size, but they have a very different slope, indicating that actually the strain in this sample is higher in this one. And that is consistent with the sample history, with the way how we treated the sample. Okay. So this is an example of application of Williamson hot plot. This is was a paper from Manson's group. It was done a long time ago, 10 years ago. And this was also on the high voltage spinel. And what also did in this paper was actually he used different annealing methods. So this is so-called HDS, this highly disordered spinel, which means that actually the sample was quenched. So up hitting to 980 degrees something, he simply shut down the furnace, and it cooled down very quickly. It was kind of sort of quenched. But for other processes, he simply controlled the annealing process. For example, is it 10-hour cooling down, or 2 days cooling down, or 3 days cooling down? So by controlling that part, he was able to synthesize the high voltage spinel with the different degrees of ordering. So DS stands for disordered spinel, annealed disordered spinel, and highly ordered spinel. So we see that when he annealed the sample for a very long time, about 4 days, which is extremely long, and for a very long time, actually, he obtained a sample that was very little strain. And in fact, this also relates to the crystal structure. And you will see that in this so-called highly ordered spinel, the nickel 2+ and manganese 4+, they start to form sort of ordering. And so actually that would lower the global symmetry of the crystal. And in this case, there's no ordering between the nickel and the manganese. Actually, they're kind of randomly distributed. And that gives rise to a lot of strain in the crystal, because the size has a lot of big mismatch, right? Nickel 2+ is big, and minus manganese 4 plus is small. So if the random distributed, actually there will be strings unreleased. There's some complications, as I mentioned. If you always interested in plotting the peak width as a function of 2 theta, sometimes you will see some very abnormal situations, as in this case. And so what we see here, this is a charged sample, this is a charged NMC, right? So if you plot the peak width of charged NMC as a function of 2 theta, you see that you do have a lot of peaks, following on the trend, right? They generally follow that at higher 2 theta, you have a broad peaks, and they seem to be on the same trend. But there are certain peaks that deviates very far from this kind of general trend, and this is so-called anisotropic broadening, right? So meaning that you have much broadened peaks, but only for a certain set of HKL peaks, and that's why it's called anisotropic broadening. So you have this sort of anisotropic broadening peaks, and when this kind of things happen, in fact, it's a good indication that something more complicated than is happening in your structure. For example, in this case of charged AMC, this kind of anisotropic broadening happens because we would have a lot of stacking faults in the charge state. So, and in fact, by simply examining how the peak width changes as a function of 2 theta, we already get that kind of hint. But surely we can go to the more depths, more details by trying to model what kind of stacking force we would have in the charged AMC. Right? So, but this could be a good beginning as some sort of hint. Okay, some of the books I mentioned, I think this is something we've talked about many times. International Tables for Crystallography, the Bible for the crystallography study. Okay, and I'm not sure how long we have been talking. If it's 30 to 40 minutes, I'll stop here.
Yeah, I think it's around 40.
40. Okay, then I'll just stop here and reserve some time for questions if there's any. Okay, I'll stop. I'll just leave the slides on, and please ask questions if you have any.
Yeah, actually, I have several questions. Thanks so much for the talk. So the first question I have that I can't remember that you mentioned the neutron doesn't have the peak shape problem. And could you elaborate more, like why it doesn't have the problem?
Frankly, I don't know why, but there's a reason. It's something that I don't know. But the fact is, the neutron-based peaks, they're typically very Gaussian. They're unlike the X-rays. My guess or my understanding, it relates to the radiation source, right? Apparently, a neutron and X-ray have a very different radiation source, and also relates to the specific optics or the beamline geometry. But those are my guesses. I don't know the specific reason why it's the neutron is typically more Gaussian.
Okay, thank you. Okay, my another question is like, cause like the number FCJ correction is for the asymmetrical correction. Like, I'm wondering why the low angles peaks is more asymmetric compared to the.
Yeah, that's a very good question. I think maybe some time ago I was able to answer that, but frankly I forgot. But if you go to the original paper, this original paper, I remember they described at the very beginning of the paper, how the asymmetry arises. My impression is also relates to the setup of your detector. How your the detector, especially diffraction geometry, all those things actually come into play when we analyze the detailed peak shapes. Yeah. If you have time interest, I think you can find the answer in the original paper.
Thanks so much.
And
That's
also you can pay attention to the slides from Brian Toby. You know, Brian Toby is actually advocate over rural refinement. Brian Toby, he is actually author of the GSAS interface. So GSAS was originally command-based. People can only type command, you know, to do the refinement. And Brian Toby wrote the interface, which is GSAS GUI, right? So actually, and there, I think he has several slides explaining why their asymmetry arise. And also, if you want to sharpen your skills in X-ray diffraction further, Brian Toby is a name that you always want to pay attention to. Brian Toby actually came from the same group with Simon Beninge. You know, Simon Beninge is a kind of a pioneer for the PDF. And Brian Toby had a lot of overlap with him, and they stayed in the same group for a long time. And Brian Toby he was mainly actually, in terms of software, he was mainly, you know, advocating GSAS. And there are people from UK, John Evans. You know, he's mostly working with Alan, advocating Topaz, right? So you know, they had belonged to different branches. But Brian Toby himself is also very serious and I think very responsible, because he had a lot of excellent discussions on the accuracy of rural refinement. For example, people have been using their RWP value, RP value a lot, right? People sometimes show, you know, I have a very small RW value, so you see how excellent my filling is, but it may not be the real case. And so he have a lot of very honest and insightful discussions on those. And also Brian Toby is also very into the total scattering. And so I would say, you know, here's some name that that you should want to pay attention to if you want to go to the more depths. And also, as a personal experience, he's very friendly. When I was PhD, actually, I was not I was kind of a blatant, and you know, I just asked questions to a lot of people and not really care if they answer. And one of the people I buzz a lot is Brian Toby. So especially when I was using GSAS at the time, I asked him a lot of detailed questions, and he always answered with a great patience. But I'm not sure if he's still patient, right? But yeah.
Yeah. Thanks. Hopefully he is. Yeah. Right. Thank you.
Yeah.
I have a question, if we have time.
Yeah.
Could you please go to the slide that has the example of peak width variation?
This one?
The plot that you showed. I'm just trying to understand the measured peak intensities. So the calculated peak intensity shows that the full width hub maximum is actually bigger than either the Gaussian or Lorentzian. So I'm trying to understand like how the combination of these two can give you a wider peak than either of the functions, because when we saw that plot that's showing the function, how the curve looked like for Lorentzian and Gaussian, Lorentzian was the one that has the highest width. So I was wondering, maybe a combination of both of these functions should lower the peak width rather than raising it.
I'm not sure if I understood the question correctly, but one thing I need to clarify is, you know, for each peak, let's say, for example, for this peak, right, the actual peak width is here, but it has a contribution from two components, and one is from the Gaussian, so that's how much it is, and the other is from the Lorentzian, and if you add them together, right, but after multiplying a coefficient, you obtain this.
I see. So the coefficient for one of these functions have to be bigger than 1, so that the combination of those two actually gives you a higher full width at half maxima. Because if it is less than 1, then the peak intensity should go lower than either of the functions.
That's right. Yeah. Okay. I got your point. Yes, that's right. Yeah. So what the software does in obtaining this kind of calculate actually is to obtain that coefficient. But yes, you're right. It should be less than 1. Yeah.
Okay. I have just one more question about the correlating the peak shape with probably with the presence of defects. So yeah, I mean, like in general, so this anisotropic broadening has been in cases attributed to stacking faults. I guess Kumaba also have a paper on a sodium cathode material related to that. I'm just wondering if the peak shape or some distinct shape of the peak could be attributed to some distinct defect in the material other than stacking faults, maybe some other type of defects like twinning, or maybe some 1D defects or 2D defects, not just the stacking faults.
Yeah, it could be. In this case, if this is it's actually the 1OL broadening, right? You see all the 1OL peaks actually they're more broadened than the other peaks, and the people reached the conclusion that is contributed by stacking faults because by using some software you can simulate how the stacking faults would influence your X-ray diffraction pattern. So in the case of AMC, you can assume a certain type of stacking force, and it's very easy to see that they will give rise to the broadened 1OL peaks, right? But in other situations, for example, like I mentioned, if the twinning of the green boundary is the origin of the faults, I believe there are also tools out there that you can use, right? You can try to simulate, but in those situations, my feeling is the phenomenon may not be that obvious, because when you think about the stacking force, it's actually it's some sort of fault at a large scale, right? So if you have stacking force, that's basically a large rearrangement of atoms. But when you have the twinning of the green boundaries, actually, their contribution total X-ray diffraction may not be that easy to tell. That's my guess.
I see. So I guess those would be easier to find out from electron diffraction.
That's right. That's right. Yeah.
Okay. Thank you.
Yeah.